Suppose we have the vector f of ti plus g of tj plus h of tk. So this is a vector in 3 dimensions that is a function of time. And we want to integrate this vector with respect to time. Now, since integration is really just the limit of a sum, we are essentially summing vectors here. And as you know, we can sum vectors in different ways. We can just sum all the I components, then the j components, and then the k components and put them together. When we are summing the I components, we're just looking at the scalar in front of I. We just sum all the scalars in front of I. So I is just a constant vector that we can take out, similarly for j and k. So here's an example. Here we have the vector r as a function of time. And we want to integrate this vector from 0 to 1. So we just go along and integrate each component from 0 to 1. So each of these integrals is straightforward, and we end up getting 3/2 I plus 1/3 j plus 2k. Let's take this trajectory example. A particle is launched with an initial velocity u at angle theta to the horizontal. Of course, a force has to be exerted on the particle to launch it, but as soon as the particle has been launched, as soon as it leaves this point here, the only force acting on it is gravity. That force vector is pointing vertically downwards. If we take directions up as being positive, then the force of gravity is a vector pointing down. It will be a negative vector. Unit vector j is pointing upwards, so we have vector minus mj pointing downwards. So j is just a unit vector, and mg is the force of gravity on the object, the weight of the object. M is the mass of the object. So we're ignoring air resistance. We are assuming that as soon as the object is launched, the only force acting on it is gravity. So this is the only force acting on it. By Newton's second law, the rate of change of momentum of the object with respect to time is the resultant force. So we have a vector equation here. So the rate of change of m times vector v with respect to time. Now we have to integrate this to get v as a function of time. So we have to integrate the right hand side with respect to time. So we ignore the j, we treat that as a constant, just like we saw in the example. So we're just integrating this here. Well, we divide both sides by m first of all. We're assuming that m isn't changing, so we can cancel m from both sides. So basically we have dv equals minus gj dt, and when we integrate both sides, dv becomes v plus a constant, and the right hand side becomes minus g times t, since minus g is just a constant, the acceleration due to Earth's gravity. So we get a constant of both sides, and that constant is a vector. We're dealing with a vector equation here. So we just bring the constants to the right hand side and just put them together and call it c. Now the velocity vector is always tangential to the trajectory, so when the mass is here, the velocity vector will look like this, going in this direction roughly. So vector v is a sum of these two vectors. Now minus gt times j is a vector that's pointing vertically down the way. Here it is. It's in the negative j direction, and when we add this vector onto some vector c, we get vector v. So in this case, for this position, vector c must be somewhere around here, so that when we take the sum of these, when we take the sum of this vector and this vector, we get vector v by the parallelogram law. It's just a rough sketch. Now the velocity vector is the rate of change of the position vector r with respect to time. We could write vector r of t like this. It has an x component which we will call r sub x, and that's a function of time, and we have a y component r sub y of t. And if we differentiate this, well, we just differentiate each component. The reason why we can do that you will see if you go through this from first principles, but I won't bother doing that here. Anyway, if we differentiate this component, the rate of change of the x component of t with respect to t can be called v sub x of t, and you know, we get the other component will be v sub y. I won't write it out here, but we've I here and we've j here. So we get v sub x times I plus v sub y times j. That's our vector v. So now we can get r, the position vector, as a function of time by multiplying both sides of this equation by dt and integrating. If we integrate dr, we get r, and a constant of course, but we bring that constant over to the right hand side. We want to integrate the right hand side with respect to t. Well, j is a constant vector, so we leave that to one side and we integrate minus gt. So we integrate with respect to t, so the minus g is just a constant. So we get for the t we'll get a half t squared. Since c is just a constant, when we integrate that with respect to time, we get that constant vector c times t, and we get a new constant vector from this equation, which we will call d. Now we have certain initial conditions here, so if we go back to the diagram, at t equals 0, the initial velocity is vector u. The initial position, the r vector, is 0, because the r vector has its tail at the origin. So in general, if the particle is somewhere along the trajectory, the r vector has its tail at the origin, of course, and its head at the position of the particle. So when the particle starts, its position is 0. So at t equals 0, we can plug in these two conditions. So okay, plugging t equals 0 in here, these two terms disappear and we're left with r at 0 equals d. So since r at 0 is 0, d must be 0. So d is actually the position vector of the particle at t equals 0, and it's 0 in this case. Now if we go back up here, the velocity dr dt is equal to u when t is 0. So if we plug 0 in here, this term disappears and we're left with vector u equals vector c. So vector c is the initial velocity of the particle. And we can get the components of this vector, since we know the initial launch angle theta. We see that the horizontal component is the magnitude of this vector. Let's say the magnitude is u, so it's u times the cos of theta. That's the horizontal component. The vertical component is u times the sine of theta. So we can actually write vector u as u cos theta times unit vector I, which is pointing in the positive x direction, plus u sine theta times unit vector j, which is pointing in the positive y direction. So we have these I, j basis vectors. So u cos theta is the magnitude of this vector here. So we multiply by I to actually get the horizontal vector that makes up vector u. And we multiply the magnitude of the vertical component u sine theta by j to get this vector here. And we add these two vectors by the triangle law to get vector u. So here is vector u cos theta I plus u sine theta j. So we can plug that in for c. D is 0, of course. We can take all the I components to one side. Well, we have to multiply t by this, so we get ut cos theta I plus ut sine theta j. And the I component is ut cos theta. That's the only I component actually in vector r. As for the j component, well, we have minus a half gt squared. And we also have this here, well, after multiplying it by t, so that'll be ut sine theta. So that's what we have here. So now we have the position vector as a function of time. We can show that the path of the particle is a parabola. Now, to do that, we just need to note that the x component is ut cos theta and the y component is given by this. So the coordinates of any point on the trajectory are given by x comma y. So here's vector r. So it's x is this here and y is this here. So we want a relationship between x and y. That'll give us the equation of the trajectory. Okay, so we see we have this parameter t. Well, we can eliminate that to get the relation between x and y. Make t the subject of this equation and just plug this in for t in the second equation. Okay, so this is straightforward. We have x over cos theta goes in for the t here, and we get sine over cos, that's tan. And over here we have to square this, we have t squared. We see that this is the equation of a parabola. It's a quadratic equation in x. The The tan of theta is just a constant because theta is the launch angle, that's fixed. U is just a constant. U is the initial speed of the particle. So this has the form of a quadratic in x, which means that its graph is a parabola.